Hey people, I'm going to introduce to you three equations that are referred to as the kinematics equations. Now, my students start the year in a place different from this. Most physics students, lots of first-year physics students start with this, and their development can either be um, come at from some different places than I'll come at them, or they're just presented to you and you learn to use them. But here we are. So the first one is not anything different than a definition rearranged, and that definition is of average acceleration. And that definition is delta V over delta T, or simply T. Now, this can be written, so that's just a definition of acceleration. Acceleration by definition, average acceleration, the rate of change of velocity. We can write this differently if we want and say delta V is AT. I'm going to drop the average. All right, these all assume constant acceleration. Okay, I can write delta V as V final minus V initial. Now, College Board notation is not to use F and I, but to use no subscript for final and to use naught for initial. And we can rewrite this to say V naught plus AT. This is the first of what a lot of people call the kinematics equations. All right, and like I said, it's nothing more than the definition of acceleration rearranged, but it's written in such a way that it looks a little different. And what we can say is, if you want to know something's velocity at some instant, you have to know the velocity that it started at, and what rate of change the velocity had, and for how long the velocity changed. Fair enough? Okay, there it is. Now, our next one comes from things you already know, and can come from a couple of places, but I'm going to write it, I'm going to do it, excuse me, for all this. Get rid of those nasty arrows. I'm going to come at it from here. We can say that if, notice we're talking about things that accelerate, right? And that can come from the fact that work is done on an object, all right? And that can come from the fact that, well, if something has a force applied to it over some displacement, well, that can make an object change kinetic energy. All right, now this is net, and this is net also. Okay, so the net work done on an object, or the work done on an object by the net force, by definition will change the object's kinetic energy. All right, so if we go from here and say net F equals delta K, I'm going to just, so, sorry, not net F, but net F, but net F times delta X equals delta K. Well, net F can be written as MA, delta X. And here's, let's see, K final, 1/2 MV final squared minus 1/2 MV initial squared, except I'm supposed to use College Board notation where we don't use F and I, we use no subscript and naught. Notice we can divide every term by M. I can multiply every term by 2, and what I get is 2A delta X is V squared minus V naught squared. And if I move things around, I get this. That is the second of the two kinematics equations. Now, unlike this one on the left, which says, hey, you want to know how fast, or you want to know what an object's velocity is at some instant, you better know what its velocity was and for what amount of time it accelerated at a certain rate. This one says, hey, you want to know what something's velocity is? You better know what its velocity was and over what distance it accelerated at a certain rate. Okay, so the difference being, are we talking about acceleration as it occurs over time or acceleration as it occurs over space? And why have two different ones? Well, in different scenarios, you might not know for how long something accelerated, but you might know over what over what change in position the acceleration happened, or vice versa. Okay? Okay, so there are two kinematics equations. Get rid of all this ugliness. Now the third one can be come at in the context of a graph. All right, now, a couple ways to do this, but what I'm going to say is this object has some initial velocity we'll call v naught. It has some final velocity we'll call v. And this acceleration that you can see happens over an amount of time that we'll call t, or delta t, or t, it doesn't matter. Now here is delta v from v initial to v final. All right. And what it's important to know is that you can find from this graph change in position. Change in position is v average times t. Now there's a couple ways to express v average, but what's also important to be able to note is if we, don't draw this quite yet, watch this part. The v average, because this is a constantly varying function, the velocity as a function of time varies constantly, the average value of v is right there. And so if we do v average times t, that's the same exact thing as finding the area of this shape. So one thing that's worth noting is that delta x can be found by taking the area under a VT curve, which is really to say the area between the curve and the x-axis. That's worth noting. Now, what's also worth noting, again, don't draw, but look at this. If we went back to this function, notice there's some extra area here that the blue rectangle has, but some extra area here that under the green function. And those two triangle areas are the same area. And what that says is if we get rid of all this stuff, that the area under our original function is the same as the area of this v times t, this v average times t. All right, the area, I'll do it one more time. The area of this rectangle is the same as this area, the area of this whole shape. So the question is, what's that area? That area, delta x, is that area. And that area can be broken up into two parts. That area can be broken up into this part and into this part. Now, so I'm going to say this. How about I say area total. And so this delta x, I'll call it area 1 plus area 2 to stay with my color coding. Now, the area of the red part is the base t times this height v naught. So we can write that as v naught times t. Maybe I'll stick with my color coding, v naught t. Now the area of the blue triangle is 1/2 base times height, right? It's a triangle. So that's 1/2. The base is t, and the height is delta v, right? This height of this triangle is delta v. Well, how big is that delta v? That delta v, by definition, watch this, we can say that a is delta v over delta t, so the delta v is a times t. So this says that our delta x is v naught t plus 1/2 t at. Our delta v is a times t. And this we can then put into our final expression our third kinematics equation that says v naught t plus 1 half a t squared. So this is different. This one's not about, hey, you want to know how fast something ends up going? Notice this has nothing to do with final velocity. The first two relate initial velocity, final velocity, acceleration, and either time or displacement. This one has nothing to do with final velocity. It says, hey, you want to know how far something went? Well, you better know how fast it was going in the beginning, and you better know if it accelerated or not, and if it did, for what amount of time. Notice that if a is 0, if this thing does not accelerate, this thing agrees with stuff we've said before. If a is 0, we get delta x is v times t, v naught, right? If it doesn't accelerate, its initial velocity stays as its average velocity, and sure, that works. That agrees with what we've said before. Okay, if it does accelerate, what we get is this extra term that accounts for how far it went, how much farther it went because it sped up. Okay, so those are what are called the kinematics equations. And we'll talk about intricacies of those specifically, really important. Delta x is a vector. V naught is a vector. A is a vector. And those things play very importantly into problem solving when direction has to be accounted for. If something is, say, initially moving to the right but accelerating to the left, well, one of these terms, one of those, either acceleration or velocity, better be negative, right? Same thing here. This velocity is a vector. So is this. So is this. These are vectors. The squared part is going to kind of get rid of the vector nature of the velocity here and here. But this certainly is important if objects are moving and accelerating in the same direction or opposite directions. So again, we'll get practice with those, but that's the development of what are called the kinematics equations. Thank you and good night.